My name is Clement. I am a medical statistician at the Nuffield Department of Medicine at Oxford University. And prior to that, I was a clinical trial statistician at Imperial College. And then I had my PhD and my postdoc at Cardiff School of Mathematics and the Oxford Statistics Department, respectively. So today we are going to talk about the Introductory Statistics Session 2. So we've already done the Session 1. So if you've not watched that, the videos are out there, and then I think you should watch that before you attend to this. So just to recap some of the outlines. And so basically, again, we just touch a bit on the upcoming or the ongoing stats teachings and also future plans. And then today we are going to introduce very interesting statistical applications. One that probably are some of which are less used most of the times in most health studies. However, if you look at the nature of the data that are collected, these kind of models kind of suit those studies in the best possible way. And so today we are just going to learn about the awareness of such models, and I'll try as much as possible to be less technical, and there'll be quite a couple of examples so we could appreciate these methods. So today we are going to touch about hierarchical regression and then how people confuse that for multi-level regression. So we'll touch a bit on that. And then we touch a bit on structural equation modeling. Maybe you've heard of it, you're not too sure what it entails, or probably you've heard of it, but depending on your study, you never thought it could suit into that. So today we are going to learn and see if indeed you could also adopt that for your studies. So as I said the last time, using the right tool for the right job is always imperative. And depending on your research questions and its complexity, sometimes you might want to use some of these advanced methods. And then we are going to touch a bit on time to event analysis, properly known as survival analysis. And in this case, we're going to look at the case of stratified versus unstratified, and then learn about an extension of the standard survival models, which we call the multi-state Markov model. Because of time, I couldn't touch on one other advanced method, which was very keen for me, and that is called functional data analysis. I'll just do the concluding remarks on that. Okay, so once again, last week we did the introductory stats 1, which is basically talking about a brief overview about some of the most important and basics and terminologies and things you need to know about statistics, and the fact that your data, the type of variables could have impact on the kind of analysis you do, and can even inform your choice of statistical methods and so on and so forth. And then we did that in the case of parametric, non-parametric, multivariate versus univariate, and so on and so forth. So if you've not watched the first video, I think you would want to watch that. So today we are going to introduce the star session 2 and repeat it on Friday as well. And once again, for future sessions, we are planning of hosting or having this kind of interactive session where a researcher or a group of researchers will present the statistics bit of their works, get feedbacks from not just me, but also within a team in the case of brainstorming, and then for others to also learn about other methods that people are using out there across different disciplines and different subject areas. So this is something which is still on the developing stage, and then so we'll still need your feedback to know the best way we should approach it. And we're also thinking about some drop-in sessions as well, which is still in the developing stage. So your feedbacks are really, really needed. So without wasting time, we'll just go straight. So first of all, so today we are going to talk a bit about the first one is hierarchical regression. So we realize that in our previous sessions, we talked about linear models, and we realized that linear models kind of looks at the one-dimensional effect of some set of predictors on the outcome variable of interest. But there are instances where we are interested in knowing the individual contribution of each of your predictors or some specific predictors in terms of explaining the amount of variability in your outcome variable. So hierarchical regression is a way of trying to model. It's more of a model comparison rather than a typical statistical method per se. So meaning that this concept can be applied to fixed effect models, can be applied to mixed effect models, and so on. So what we mean by nesting is that, so with the hierarchical regression, it's more like instead of putting all your predictors into the model and looking at its effect on the outcome, you want to do that in a stepwise fashion. And that stepwise fashion is what basically we are saying hierarchical fashion. So that gives the name hierarchical regression. So for instance, if you look at this case, so let's say I have about n predictors, and then we are trying to look at how they predict the outcome. And just to break it down, so let's say you have 3 predictors, and then you want to see how those 3 predictors affect your outcome variable. But you're also interested in also identifying the individual contribution of each of the predictors on the outcome, or you are even interested in identifying potential moderators and mediators that could exist. I'll touch a bit on moderation and mediation later. So hierarchical regression helps us to achieve that. So in a way, it's a model comparison technique, but at the same time, trying to look at the individual contribution of some of your predictors or set of predictors on the outcome in terms of the variability it explains in the outcome variable. So let's say we have 3 predictors, and then you put the first predictor into the model. People can assume that it's a type of a stepwise regression technique, but this time around, you realize that you are going to build a series of models where the second model, the second model contains the first, and then the third model contains the second, and so on and so forth. So that's what we mean by nested regression models. So if there are 3 predictors, and I start the model with the first predictor, and I check how the first predictor affects the outcome variable. And then at the second step, and I compute the R square. So in this case, the R square is just the amount of variability explaining the outcome. And the greater the variability, the better. And then we go to the second step, and then we add a second variable. Sometimes you could add a set of variables, but I'm just using a simple case. So you go to the second step, you add the second variable, and then you now assess or compute the R square and check if there was a significant change in the R square. Keep in mind that automatically adding a second variable would automatically increase the R square. So basically, a model with 3 predictors would have a higher R square with a model where we've taken one of the predictors out of the 3. So basically, the higher the number of predictors, automatically the higher your coefficient of determination, or the R square. However, even if the predictors are insignificant or not. So basically, after adding the second variable, we assess whether the change in the R square was significant. And if it was significant, then it tells that the addition of the second variable improved upon the variability explaining the outcome variable. And then we go on to the next step, where we can add another variable and then also assess whether there is a significant change in the R square. So you realize that we started with the simplest model. Sometimes you could even have a model without any predictor, and then you add a predictor, and then you further add a second predictor in that fashion. Sometimes you could add a set of that. But one thing that it also achieves, apart from model comparison purposes, and also apart from knowing the individual contribution of these predictors on the outcome, we can also identify something called potential moderators and mediators. I will explain that. But now think about it. So let's say we added a certain predictor into the model. And upon adding the second predictor, if the first predictor in the model was previously significant or not significant, and after adding the second variable, it caused it to be significant, then it tells that the second variable, in the presence of the second variable, the first variable was significant. And that could be a potential mediating variable, and which we would have to do a formal test to ascertain that. And then there are instances where after adding the second predictor, it's if the outcome variable was already, insignificant, and then it caused it to be significant, or it was already significant, but the addition of the third or fourth variable caused the previous to be insignificant. It also gives us another insight. So this is to say that hierarchical regression is, apart from the fact that it's useful for assessing individual contributions of predictors on your model in a stepwise fashion, it also helps us to identify a potential moderator or mediating variables. And then these will be useful when we talk about structural equation models. So most of the times, to even do a structural equation model, you can couple hierarchical regression with moderation and mediation analysis. And then that will help inform your structural equation model rather than just going into it without any knowledge of the potential structure, or probably trying to rely on literature to get your structural equation model. Yeah, so this is just to explain what we mean by hierarchical regression. So the key term is that it is just nesting set of regression models, not about the data. So it means hierarchical regression in this case, the data was already cross-sectional, but we're just modeling or adding the predictors in a stepwise fashion whilst exploring or investigating the change in the amount of variability explaining the outcome. And remember, then the more or the higher the variability explained, the better your fitted model. So, and then we also know some of its importance. So now, one take-home message is that most people call multi-level regression, which is also known as mixed effect models. So you realize that mixed effect models, if you came for the previous or watched the previous video, we said mixed effect models are often used for data that are longitudinal in nature, or data that have some hierarchical structure, meaning that if you think about, let's say, collecting data about individuals, where those individuals were within, let's say, some institutions, and then those institutions are found within some regions, and then those regions are found within some countries, those countries are found within some continents, and you have data about all these variables. Though these are variables you're not really interested in, you have some specific predictors that you are trying to check how it affects your outcome variable. But your data was naturally nested such that we have this level of nesting that looks like graphically like something like this. So that is to say that when you talk about multi-level regression, the emphasis is on the data. So if the data is hierarchical in structure, then multi-level, so the multi-level has got to do with the data, not got to do with the model itself. So this is to say that hierarchical regression talks about nesting regression models, whilst multi-level regression talks about trying to model a data that is hierarchical in structure. So some people call multi-level regression as hierarchical linear model. So if you think about it, one could also have a hierarchical multi-level regression. If you now decide not to put all your predictors into the model at the same time and decide to do it sequentially or in a stepwise fashion, trying to also ascertain the individual contribution of a certain second or a certain third variable or a set of variables to the outcome variable. So that is to say that whenever you hear multi-level regression, it's the same thing as mixed effect models, and other school of thought call it hierarchical linear model. So don't confuse the hierarchical linear model to the hierarchical regression, although the hierarchical regression is also linear in nature because we're just using the linear models, just that it's all about the way we are entering the predictors into the model. Yeah, so the take-home message, the clear distinction is that hierarchical regression focus on nesting regression models to look at the individual contribution of predictors, whereas hierarchical linear model or mixed effect model or multi-level models rather tries to model a data that has hierarchical structure. And the hierarchical structure has got to do with how the data is nested. Yeah, so basically that is the clear distinction with that. So now let's talk about the concept of moderation and mediation, since it's very important. And most of the time, we ignore these concepts in most health studies. But those studies involving psychological, most psychological studies or studies in psychology, they are very keen on always investigating into mediation and moderation and so on. So now, what is let's start with a mediator. So imagine you have a model, a regression model, where you have your independent variable and you have your dependent variable. You're trying to check how your independent variable or set of independent variable. Now let's just focus on one independent variable, and we are looking at how it affects the dependent variable. But imagine you put this predictor into the model, and then the predictor is not significant. But after adding a third variable, that third variable caused that predictor, which was insignificant, to be significant. So if you think about it, that is why I was saying that hierarchical regression could sometimes give us a fair idea about potential mediators, rather than trying to go into the literature to check, okay, given this set of variables, maybe you have utility scores, you have, let's say, fatigue scores, and so on. And maybe literature has found out that this particular score mediates the relationship between these two. Sometimes, or most of the time, let your data inform your choice as much as possible. So it means that if you can actually learn from your data to inform some of these things, then referring to literature might not be necessary, because although literature is important, if you think about even the sampling distribution of the mean, for instance. So this is just to say that although the literature is important, your data can tell a different story, completely different from the data they use to infer or to inform that literature. So this is to say that a mediator or a mediating variable is simply a variable that causes an independent variable that was previously insignificant to be significant. This is to say the independent variable can only be significant in the presence of that mediating variable. So that is one take-home message. And then we have a moderator or a moderating variable. So a moderator or a moderating variable is rather a variable that rather increases or decreases the strength of association between the outcome variable and the predictor. Okay, so it means that upon adding, so if you look at the hierarchical regression I was trying to explain, so if we've already put, let's say, the first predictor in the model, and now we are adding a second predictor into the model, and the goal is we are doing it in a stepwise fashion. So we now add a second predictor, and then we decide to ascertain the change in the R square, whether the change is significantly higher or significantly lower. As I said, it will automatically increase, but the increment might not be significant. So, but if the increment is significant, then it means that the second variable we added has increased the strength of association between the independent variable and the dependent. So it means after adding a second variable or a third variable or any other variable, and rather significantly increases the R square, that variable could be moderating the predictor and could be moderating the relationship between the predictor or the predictors in the model and then the outcome variable. But it doesn't necessarily imply that would hold. So you have to now do a proper test. So that gives you more like a qualitative idea that this particular variable could be moderating the strength of. So in terms of the strength, it means it can also either change the direction as well. So apart from significantly increasing the R square, so it's possible that your previous predictor had a negative effect on the dependent variable, but after adding the third variable, that is the moderator, it changed the direction. So at first, if the effect size was positive, it's probably in the presence of the moderator, it changed the effect size to be negative, and so on and so forth. So this is just to say that moderating variable do not only increases or decrease the strength of association, but they could also predict or change the direction of association as well. So that explains why hierarchical regression is useful if you really want to start thinking about moderators and mediators in that light. And then that will give you like a fair potential candidate. And then you can now do a proper moderation mediation analysis to investigate that. In most softwares, they have moderation mediation analysis. One popular method is called the Anderson-Hayes test. That is a moderation and mediation analysis, which you can read more into that. So now with the knowledge of moderation and mediation, you can now talk about structural equation modeling. And now let's see how this structural equation modeling could even inform the kind of studies you've already been doing, or maybe you've already done a study. You might want to reanalyze the same data to now identify more or complex association rather than the invariant associations or the one-dimensional associations. Yeah. So if you think about the regression, the linear regression I was talking about last week, you realize that you're just looking at the one-dimensional relationship between the dependent variable on the outcome and between the predictors on the outcome variable. And then we said that situations where we have multiple dependent variables, you might have to now use a multivariate regression and so on. But there are instances where not every variable that we want to actually measure, or not every predictor can actually be measured, or not every dependent variable can actually be observed. So what that means is that it introduces us to some set of variables called latent variables. So latent variables are variables that we cannot observe them, but we can only quantify them through some observed indicators. So if you think about it, utility score, which we mostly use in clinical trials and in most studies. For instance, the EQ5D scale, that's though it's a scale that trying to just quantify one's utility score, which is a measure of health status. But remember, that is not like a true score. It's just something quantifying that. Yeah, so it means that scale trying to quantify. So it makes utility score a latent variable because we cannot measure it. For instance, if I want to measure your blood pressure, I can measure it directly. So it means blood pressure is a data that can be observed, but I can't really observe your health status or I can't really observe your utility score until I use some construct to measure that. So that is what we mean by latent variables. And then the observed variables are those variables you can observe and you can measure directly. So in structural equation model, what it does is that it combines two principles. It combines path analysis. By path analysis, we mean regression. So regression is just a form of path analysis. So it combines path analysis and something called confirmatory factor analysis. So if you think about factor analysis, we have two versions. We have the exploratory and we have the confirmatory. So with the factor analysis, we have this structure. And the goal is that we want to know whether that structure is going to hold or not. And in the structure, just like this structure we have. So it means that now, let's say, if you look at this particular diagram, social, I don't want to give the details, but this social score, intellect score, motivation score, basically, we are trying to look at how it predicts job perfection or job performance. And at the same time, so it means at this case, this is like the outcome variable to these three variables. But this is also, we are also trying to see if job performance could also predict these ones, which are, yeah. So in structural equation model, when you see the square or the rectangular objects, basically they are the observed, and then the oval shape, or if you want to call it the circular shape, represent the latent variables. So often that is one clear distinction to know. So anytime you see a variable in a square, in a rectangular shape, that is an observed variable, meaning a variable you could easily observe. Like this one is, yeah, I mean, some test scores and so on, their IQ, their years of education. So it's in the square, it's in a rectangular box because we can observe them. And then the ones that are in the oval shape or circular shape are the latent variables. So in terms of confirmatory, in terms of factor analysis, so we always have this structure. So it means that this structure, someone would want to now propose a structure based on literature. So the moment you propose a structure, it means that at that instant, you are just exploring. So in that case, you are trying to now do something called exploratory factor analysis. But the moment you now want to confirm that structure to know whether indeed this intellectual score should be where it is or not, in that case, you are now trying to confirm. So the moment you now decide to confirm the structure, then you are trying to do the confirmatory factor analysis. And that explains why hierarchical regression can sometimes become like a baseline or a base exploratory analysis just to have a fair idea the kind of structure you want. And of course, you can always also use literature to inform that. Yeah, so basically what structural equation model is trying to do is that we are now trying to not model just a one-dimensional association between the predictors on the outcome, but now we want to be able to explore complex relationships between not even a single dependent. Of course, it could be a single dependent, but it could also be a set of dependent variables, and even look at how those dependent variables correlate with each other, whilst as also investigating even relationship between the latent variables and so on. So it means that anytime you want to know more about your data, because most studies, we just do a simple linear regression, and then you just say that, oh, okay, this set of predictors or this particular predictor is significant, and these ones are not significant, and that is it. And that is just a one-dimensional relationship. It's possible that that variable that was not significant could be significant in the presence of a third variable, or could be significant if you had done it in a hierarchical fashion. You could have even realized that it was because of a certain other variable that caused it to be insignificant. But we don't do that. We just put these predictors into the model and just look at that one-dimensional relationship. So this is just to create the awareness that we can always also investigate more complex relationships. And most of the time, it even helps us to answer very complex research questions. So, and then if you look at most health data, for instance, we collect information. And so to use structure equation model, you have to always have at least one latent variable. So it means that some of your variables should be something that cannot be, observed directly. So if you think about most studies where in clinical trials where we quantify maybe fatigue score, we quantify post-traumatic stress score, we quantify even happiness score, we quantify emotional score, and so on and so forth, health utility score, and so on and so forth. All these are latent variables. So if you are trying to now put them in a model and looking at how they affect maybe a certain outcome variable, this is to say that with the help of structural equation model, we can even investigate more complex relationships and even test more complex hypotheses. Yeah, so this is bringing us to that awareness that we should always try to check if structural equation model can also sit well in our research questions and the kind of studies we do, because somehow it kind of fits so well. And then with that, you can investigate more complex association. And the one-dimensional regression is not always sufficient, especially if you really want to be innovative, if you really want to get novel findings, especially if you want to get very novel findings. Sometimes you have to push yourself to do some of these to note complex stuff that maybe other studies that use the one-dimensional couldn't find. Okay, so that is just about structural equation model, hierarchical regression, and so on. So now we are going to talk about time to event analysis. The name survival analysis came to be because with time to event analysis, basically what we do is that we are trying to model the time to experiencing an event. Or in most studies, we are looking at the time between entering the study until a certain event occurring. And often that time difference is what we are trying to model. And then we can also do that and see how some predictors or some covariates explains that time. And then so always there must be an event. And the event at first was, so basically the main survival analysis came in because originally we were modeling the time between treatment until death. So, and most of the studies that started these time to event analysis were always looking at the time between treatment until death, or treatment and the occurrence of death. And then later on, we discovered that we could actually extend it not just to death, we could also extend it to other absorbing events, or we could even extend it to different instances. For instance, we could even look at modeling the time to experiencing an adverse event. We could even look at the time to discontinuing from a treatment, or if a patient are on a particular treatment, we are looking at the time till they discontinue from that treatment. We could even look at the time taken for, let's say, individuals to heal from a certain infection. So it means that, and it's not just about health studies. You could apply to econometric studies, even the time to inflation occurring and the time to any event occurring can be seen as a time to event analysis. Yeah, so there are different types of survival analysis, or basically survival models. So we have the non-parametric one, which is popularly called the Kaplan-Meier survival analysis. And then we have the semi-parametric, which is the Cox-Proportional hazard model. So it means the Cox-Proportional hazard model, which we often use, is a semi-parametric. Remember, last week we talked about parametric and non-parametric models, and we said for the parametric models, they have a very strong and specific assumptions that needs to be achieved in order to be able to use them. Otherwise, doing departures from those parametric assumptions and still using those models, we are likely to get very misleading or very wrong results. And then we said for the non-parametric are quite robust to departures from these parametric assumptions. But this is to say that given that Cox-Proportional hazard model is a semi-parametric, It means that it is quite robust to some as departures from some assumptions, but it also has some specific parametric assumptions we need to achieve. So we'll touch a bit on these, since it's one of the most used class of models when you talk about survival analysis, especially in health studies. So for the parametric, we have different types of parametric models, parametric survival models. But this particular presentation is just going to focus on the non-parametric and the semi-parametric case. So the Kaplan-Meier estimate or the Kaplan-Meier survival analysis is basically, it's more of an exploratory survival analysis, in that you are only able to consider one covariate or one predictor at a time. So it means that we can investigate or explore how the survival times varies between a certain group or a certain categorical variable. So it means for Kaplan-Meier analysis, you cannot do Kaplan-Meier analysis when your covariate is a continuous variable, unless you decide to now recategorize it and then investigate into if there's any difference in the survival curves, or if there's any difference in the survival probabilities between those levels of that particular group variable. And so Kaplan-Meier analysis, most studies sees it as a univariate survival analysis. But instances where you want to now control for other predictors, or you want to now control for or see the effect of some set of predictors on the survival times, then the Cox-Proportional hazard model becomes imperative. Even the name proportional hazard gives the most important assumption. It implies that the hazard function. So basically, when you talk about the hazard function, so it's just basically looking at the quantifying the risk of, if it's the risk of death. So, and then the inverse of that is basically a survival. So here we expect that the hazard, if you consider any two individuals, we expect that the risk of death, or the hazard, should be fairly constant between any two individuals. But that assumption is often not achieved, or in most cases. So we talk about in such during departures of such assumptions, what do we do? And then there's a certain time invariant assumption that most of the covariates, especially the continuous covariates, specifically the continuous covariate, should not be time varying. This is to say that it shouldn't be a variable. It shouldn't vary over time. So it means that anytime you have some predictors in a survival analysis, where those predictors, especially those continuous predictors, can change over time, or can change within that study period or observational period, it means it's likely that the parametric assumptions of the Cox-Proportional hazard model might not hold. And so this, and then we are going to talk about, in such cases, what do we do? So remember, and then so it means that there are other assumptions. For instance, the time to experiencing the event, even if you observe it in discrete times, we assume that it's continuous in the model. So even if, because most of the times in continuous time studies, we often observe our data in discrete times, because we can't observe data within a continuous time. Often we record it in discrete time. So we assume that even if your time to the time to event outcome is recorded in discrete times, we assume it's continuous. And then we assume there's no missing values. And there's one important assumption is right censoring. So it means that for survival analysis, we expect some of your observations to be right censored. So what is censoring? When you talk about censoring, so for instance, let's say you started a study and then you have a certain end date and you have a start date. And there are certain individuals, and then we have a particular event. Maybe let's say the event is time to, we are looking at time to death. And let's say you recruited some participants, and the participants, one of them or some of them, died before even the beginning of the study. But you don't know at what time they died. That is what we mean by left censoring. And then when you talk about right censoring, so right censoring, which is one assumption for using these survival models, including the Kaplan-Meier method, is that So right centering is situations where within the observation period, that individual or those set of individual or those individuals did not experience the event within the study or observational period, but we believe that they could experience it afterwards. So and that is to say that if there's no right censoring your data, using these methods would not hold. Then we have to think about a different method. So and we believe that not all your individuals will experience the event of interest. Yeah. So basically, that is what we mean by right censoring. We have different types of censoring. Interval censoring. Someone can enter the study, and then within a certain period, it's like the individual could be lost to follow up, or we just maybe the individual exited from the study and later joined at a future date, still before the end of the study period. So it means that period where we were not too sure about whether the individual experienced the event within that interval. It also introduces another type of censoring called interval censoring. But the right censoring, where some of the individuals did not experience the event within the observational period, is an assumption that we really need to meet, especially if you want to use these Kaplan-Meier analysis and the Cox-Proportional model. Okay, so but situations where the constant hazard assumption is violated, it now introduces us to what we call stratification or stratified hazard regression or Cox-Proportional regression. So some studies or some researchers consider Kaplan-Meier as the only unstratified method, which is not true. And because so it means even for the Cox proportional hazard model, we could have the unstratified version and the stratified version. By stratification means that, and don't forget, based on the assumption I gave, we expect that the continuous covariance should not be what? Time varying. If it's time varying, it's going to affect the assumption that the base hazard or the base rate, hazard rate, should remain fairly constant across different levels of your outcomes. But once some of your covariates are time varying, it implies that particular rate or base rate could change over time. And that is something, if it's violated, then we stratify our study, or we stratify the model based on those and the stratification factor could be a continuous variable, or it could be categorical, especially if you believe that some levels of a certain categorical variable could have different, or could infer or could inform different base rates, or in terms of the hazard rate will change across those levels. Then we now use stratification, and there are more official statistical way of assessing whether those assumptions are met or not. And don't forget, Cox-Proportional is a linear model. So again, we expect a linear relationship between your predictors on the outcome. And then, so in situations where we have departures from this linearity, then what do we do about it? So we also look at that. So stratification basically is broadly for two things. Is to now it could be used to verify whether those proportional risk assumptions were met, and then in situations where they are not met, we could now incorporate this non-proportionality by stratifying the model based on those set of predictors that did not achieve those constant hazard assumption. So to make life easier, we are going to use a data, like a well-known data, to explain some of these things and look at, if you are doing survival analysis, what are some of the most important things we need to achieve or we need to also report on. So we are just going to use a data which was obtained from some Veterans Administration. And so basically it was a lung cancer data. And it was obtained from a clinical trials where patients were randomized to either receive a standard chemotherapy or some experimental chemotherapy. And then the baseline, the primary endpoint or the main endpoint was time until death. And so we would talk about, so those, so here we are, so that is basically the summary of the data. So we just talk about some of the covariates or some of the predictors or the variables that they collected in the data. So you see something called the Kano variable, which is just talking about the Kanofsky score, which quantifies patient overall baseline status. Yeah, so, and then if the score is greater than 70, it implies that the patient is able to take care of themselves. If the score is between 40 to 60, it means that the patient requires some assistance. And if it is between, and often the minimum is 10, and then it's often recorded at discrete, in a discrete fashion. And so that's why it has been discretized in that manner. Yeah, and then we have a variable called die time. So this is just the time demand from diagnosis to randomization. And then we have age of the veterans. And then we have a variable called PROW. This is just an indicator as to whether the patient will see a PROW therapy before the study or not. And then we have a variable called cell type, which is the type of tumor. So we have 4 levels of that. So this is just to say that anytime you are doing survival analysis, the first thing is to produce some Kaplan-Meier curves. So these curves are what we call the survival curves or the Kaplan-Meier